In the previous episode, we saw how eigenvectors and eigenvalues can be used to solve dynamical systems and to predict how a system evolving over time will behave in the long run. And one of the main ideas used in that lesson was that if you have things expressed in terms of the eigenvalues and the eigenvectors of the matrix, then that makes it very easy to calculate very high powers of that matrix. Because applying even something like 60 copies of the matrix A to an eigenvector really just amounts to taking 60 copies of the eigenvalue and using that to scale the eigenvector. In this lesson, we're going to talk about a process called diagonalization. And diagonalization takes this idea and just presents it in a slightly different format. This is another way to understand the relationship between eigenvalues of a matrix, eigenvectors of a matrix, and this action of taking several powers of that matrix, the matrix raised to a large exponent. So the first thing that I want to observe toward this idea of diagonalization is that if you have a matrix that is diagonal, it's very, very easy to calculate its powers. For example, if I give us this diagonal matrix 2, 0, 0, 3, let's calculate large powers of this matrix and see if we can observe a general pattern. If I call this matrix A for short, and I think about what would be involved in calculating A squared, this diagonal matrix multiplied by itself. If I go through with that vector dot product, the very first thing that would happen when this first row hits this first column is that I would get 2 times 2 and then plus 0. So I'll write it this way, 2 squared. In the corners, top row, second column, bottom row, first column, in the corners we're still going to have 0. And then the bottom right corner, when this second row hits this second column, we're going to end up with 3 times 3, which I will express as 3 squared. You might already be catching the pattern here, but just one more for the exercise if you don't see it yet. If I do a cubed, I can calculate that via a times a squared. So I can do 2, 0, 0, 3 times 2 squared, 0, 0, 3 squared. Let's see what happens when I multiply these matrices together. First row times first column gives me 2 cubed, zeros in the corner, and then bottom row, second column gives me 3 cubed. So now perhaps you see it. So if you happen to be lucky enough to have a diagonal matrix, then calculating the powers is very, very easy. If you have a diagonal matrix, the powers of that matrix can be calculated just by applying the exponent to the diagonal entries. When someone talks about diagonalization, they're talking about taking a square matrix A and writing it in the following format. Taking the matrix A and factoring it into a very specific form, a matrix P, a matrix D, and a matrix P inverse. Now, just to write down P inverse, it's implied that the matrix P, as used in this factored form, must be invertible. The matrix D, as used in this form, is diagonal. And if you have a matrix that has been diagonalized, once again, you're in a scenario where it's very, very fast and easy to calculate high powers of this matrix. If you have a matrix that's been diagonalized and you want to calculate, for example, A squared, you can do that by taking A, PDP inverse, and multiplying it by another copy of A, another copy of PDP inverse. But because we have the matrix P and its inverse in direct contact with each other, these guys are going to cancel out. So that's going to leave us with P times D times D times P inverse. And so this central matrix becomes D squared. And so that D squared in the center, that diagonal quantity in the center, it's going to be very easy to raise it to a power 2. Because for diagonal matrices, they can be raised to the power 2 just by applying an exponent of 2 to the diagonal entries. If your matrix A is diagonalized and you want to take it to the third power, once again, I can just take that matrix, PD, P inverse, and multiply it by that matrix squared, PD squared, P inverse. So we can cancel out these central terms because that's a matrix times its inverse. And so we get P times D squared times P inverse. And so we get PD cubed P inverse. And once again, this is going to be very easy to calculate because you can calculate D cubed very quickly. And so on and so forth. If you have a matrix that has been diagonalized, if you want to raise it to whatever power, a to the power n, for example, you can just do that by raising that middle portion, that diagonal matrix in the middle, to the power n. And that's very easy because for diagonal matrices, you just have to raise the entries on the diagonal to the nth power. So that's the purpose of diagonalization. The purpose of diagonalization is to take a matrix that's not diagonal yet and rewrite it so that it involves a diagonal object. We do this because this allows us to calculate large powers of the matrix very quickly and very efficiently. Let's now talk about how to do this and how to construct these matrices P and D that form the diagonalization. So the first thing that you want to do is you want to calculate those eigenvalues and those eigenvectors. The eigenvalues of the matrix are what's going to form the diagonal entries of the matrix D. Then you're going to calculate the independent eigenvectors of the matrix A, and those eigenvectors are going to form the columns of P. Let me give you a demonstration of this process in the following example. We have here this 3 by 3 matrix, 1, 3, 3, negative 3, negative 5, negative 3, and 3, 3, 1. So let's go ahead and diagonalize this matrix. And the very first thing that we're going to do is we're going to find its eigenvalues, and then later we'll find the corresponding eigenvectors. So for the eigenvalues, the normal process applies. Go into the matrix, subtract lambda from the diagonal, and then calculate that matrix determinant. For a matrix of this size and this density, 3 by 3 matrix with no zeros inside of it, I think I will definitely use computer assistance to find the characteristic polynomial. So according to Wolfram Alpha, the characteristic polynomial for this matrix is negative quantity lambda minus 1 times lambda plus 2 squared. If we set that equal to 0, this gives us two eigenvalues. Lambda 1 equals 1, and lambda 2 equals minus 2. But notice that lambda 2 equals negative 2 is in some sense repeated in this characteristic polynomial, repeated twice. So as of this moment, I have enough information to construct the diagonal matrix D in our diagonalization. If a diagonalization exists, then the matrix D would have entries like 1, minus 2, and minus 2. I would repeat that second eigenvalue because it appeared twice in the characteristic polynomial. So this is what the diagonal matrix would be. Now, a question that arises for many students is, can I put the eigenvalues in a different order? Like, can I go minus 2, minus 2, 1? And the answer is yes, you can do the eigenvalues in a different order inside the matrix D. You just have to, when you write down the matrix P, match what's going on in the diagonal. So let me demonstrate that to you in the next step. The next step would be to go ahead and calculate the eigenvectors associated with these eigenvalues. So for example, zooming in for a moment on lambda 1 equals positive 1. If I take that specific eigenvalue and I plug it into this matrix, I get 0 in the top left entry, then I get minus 6, then I get 0 again. So after row reduction, we get 1, 0, minus 1, 0, 1, 1, and 0, 0, 0. And if I think about the null space of this matrix, if I think about what's going to cause this guy to output 0, I would get x1 minus x3 equals 0. I would get x2 plus x3 equals 0. And I have a free variable in x3. So that means that the eigenspace is spanned by a single eigenvector. If I set v1 to be equal to the vector that I get by looking at the coefficients, positive 1, negative 1, and positive 1, this vector v1 spans this eigenspace. Let me do the same thing with the other eigenvalue. If I go into this matrix and I subtract negative 2 from the diagonal entries, or in other words, add 2 to the diagonal entries, I get positive 3 in the top left. I get negative 3 in the center. And then I get positive 3 in the bottom right. And this matrix is trivial to row reduce because all of the rows are just a scalar multiple of each other. So when we row reduce this matrix, everything is going to cancel out except for the row in the top, which could further even be divided by 3 to make it even simpler. So if I think about this matrix in terms of its associated null space, we would get a relationship that x1 plus x2 plus x3 has to be 0, but x2 is free to do whatever it wants, and x3 is free to do whatever it wants. We just have to make x1 match. So x1 is equal to negative x2 minus x3, x2 is equal to itself, and x3 is equal to itself. And so this eigenspace is spanned by two independent eigenvectors. I'll call it v2 comma 1. This is coming from the coefficients of the x2 variable. And then v2 comma 2 coming from the coefficients of the x3 variable. So this eigenspace would be two-dimensional, and it would be spanned by these two vectors. Now I want to notice that over the course of this process, we have achieved 3 independent eigenvectors. Earlier, we obtained the vector v1 given here, and we've just obtained the vectors v2, 1 and v2, 2 in this previous step. And since we have gotten 3 independent eigenvectors, we have enough to build a 3 by 3 matrix. And these vectors will form the columns of the matrix called P in the algorithm. The first eigenvector becomes the first column. The second eigenvector becomes the second column. And this final eigenvector becomes the third column. This is invertible because its columns are independent. So in summary, the diagonalization of this matrix, the expression of this matrix in the form invertible, diagonal, invertible, would have the invertible matrix P given here and the diagonal matrix D that we found earlier. So this would be the diagonalization of this matrix A. As noted before, if you decide to write your diagonal matrix with the eigenvalues in the other order, for example, with the 2's on the diagonal and the 1's in the bottom right corner, then you would just have to swap the columns of your matrix P to match that and put the 2 eigenvectors corresponding to -2 in the lead, and then put the eigenvector corresponding to 1 in the back. As long as it's consistent, you can order things in either way. So that's the process of diagonalizing a matrix. If you have a matrix A, start by finding its eigenvalues and its eigenvectors. The eigenvalues of the matrix will form the entries in the diagonal matrix D, and the eigenvectors will form the columns of the invertible matrix P. Now, in some cases, you will not have enough independent eigenvectors to build the matrix P. And in that situation, your matrix A simply cannot be diagonalized. And let me give you an example of a matrix that cannot be diagonalized here. 2, 4, 3, -4, -6, -3, and 3, 3, 1. Once again, using technology, because this matrix is relatively large and quite dense, let's write down the characteristic polynomial. So we get exactly the same characteristic polynomial as before, negative lambda minus 1, lambda plus 2 squared. If we set that equal to 0, then we get two eigenvalues. Lambda 1 equals 1, and lambda 2 equals -2, repeated twice. So the diagonal matrix that we would build from these eigenvalues would be the matrix that has, for example, 1, -2, -2 on the diagonal and zeros elsewhere. To find the matrix P, we would need to find the eigenvectors of this matrix. Finding, for example, the eigenvectors corresponding to specifically lambda 1 equals 1. Let's go into this matrix, subtract 1 from the diagonal entries, and then find the associated null space. So subtract 1 in the top left, subtract 1 from the center, subtract 1 from the bottom right entry. Let's use technology to row reduce this quickly. We get this reduced matrix here, 1, 0, -1, 0, 1, 1, and 0, 0, 0. So the vectors in the null space of this matrix, the eigenvectors of the original matrix, would satisfy x1 equals x3, x2 equals -x3, and x3 is free. So we would get an eigenvector, again, of 1, -1, 1. So far, very much similar to what happened before. But now, let's see what happens when we consider the eigenvectors associated with this other lambda value of -2. Let me go into my matrix and add a value of 2 to all the entries on the diagonal. So 4, -4, and 3. This matrix isn't quite so trivial as the one we got in the previous exercise, and the row reduction reflects that. We have 1, 1, 0, 0, 0, 1, and then a row of zeros on the bottom. So if we interpret this in terms of what it's saying to us about the null space, that first line says x1 plus x2 is equal to 0. That second line says x3 is equal to 0. And the third line is vacuous. So we get in this instance a single free variable. x1 depends on x2, x3 is identically 0, and so x2 is left to be the free variable. And since we only have a single free variable, we only get a single independent eigenvector, v2 being -1, the coefficient of x2, +1, the coefficient of x2, and then the third component must be at all times equal to 0. So even though we're trying to diagonalize a matrix that has 3 rows and 3 columns, we do not have enough eigenvectors to build a matrix P that has 3 rows and 3 columns. We would like to have 3 eigenvectors, but we've only obtained 2 independent eigenvectors. So we don't have enough to build the matrix P. As a result, this matrix A cannot be diagonalized. This matrix A cannot be expressed in that PDP inverse form. So that concludes today's video. In this video, we saw that if you happen to have a diagonal matrix, then you can calculate large powers of that matrix very easily just by applying the exponent to the entries on the diagonal. If your matrix is not diagonal, there is a possibility that it can be expressed in terms of something that is diagonal. There's a possibility that you can take your matrix A and factor it as PDP inverse, where P is some invertible matrix and D is some diagonal matrix. Your matrix A might not be diagonal itself, but if it is diagonalizable, then it's still very easy to calculate large powers of that matrix, because you can just apply the power to the diagonal matrix in the center of that expression. To find the diagonalization of a matrix, you need to find the eigenvalues and the eigenvectors of that matrix. The eigenvalues of the matrix form the diagonal entries of D. And then the eigenvectors of the matrix, the independent eigenvectors, form the columns of the matrix P. Now, bear in mind that some matrices cannot be diagonalized. And this happens in the case that when you're finding the eigenvectors of your matrix, you don't get enough independent eigenvectors to build the square matrix P for the diagonalization. For example, if your matrix A is 3 by 3, but you only get 2 independent eigenvectors, that's not enough eigenvectors to build the matrix P, so such a matrix is not diagonalizable.